Hello, everybody. I'm glad it stopped. Is it still not raining out there? It's not raining. I see some sun. Good. This morning was brutal, right? If you were here early, past the parking and the traffic, that rain was no fun. Okay, let's get going on this. I think we want to end up at about 3:50 here. Here's what I'm going to be covering today on the topic of AutoEZ and EZNet. As a current state of EZNet and NEC-based modeling, this is current until pretty much today. If you're interested in some of the history of NEC, I had a 2011 Contest University presentation with some history, if you're that interested. Of course, when we say NEC, N-E-C, that really stands for Numerical Electromagnetics Code. And that's software that goes back to about 1980, so we're talking 45 years here. The Wikipedia page for NEC, it has one, is a pretty good overview. And of course, this goes back to the day when input was by punch cards, right, a deck of punch cards, and output was line printer paper. And as a result, many people, especially once Windows software started coming along and graphic user interfaces, started putting shells around the NEC programs, and you could view them largely as a computing engine. Because I don't know about you, but I guess I did use punch cards when I started in college, but it was a long time ago. Okay, for many years, probably the last 20 plus years, the first question that was usually asked when it came to talking about modeling was, are you using NEC 2 or NEC 4 for your modeling engine? And NEC 2 was free, it was in the public domain, but it had some serious known limitations. But it turns out there were some clever workarounds that got incorporated into programs like EZNet and others. Now, NEC 4 was the Cadillac program, but that had a $400 license fee. And it had many improvements, far fewer limitations, and to get the license, you had to go to LLNL, Lawrence Livermore National Laboratory. And that still is the case to this day. Now, I'm pretty sure that there are various bootleg copies of NEC 4 out there that people use. I think all that probably violates some license agreements, so if you want to be strictly by the book, you need to get a license for it. Now, if you wanted to use NEC 4 with the souped-up version of EZNet, the Pro 4 version, that was an extra $600, right? So back when I got this stuff 12, 14 years ago, the investment was about $1,000. But for what it does, I think that's a great deal. I was always happy with it, you know, no complaints. Now, that, of course, goes back 45 years. There have been a few significant events in NEC and EZNet over just the last few years. In particular, NEC 4.2, which really is sort of the follow-on from NEC 4.0, was released, and then something called NEC 5.0 was released. Now, it turns out that NEC 5.0 is really based upon a different, and this is their language, not mine, electric field solution method. And so therefore, it's not just a tweak to NEC 4.2, right? And in fact, it's a separate product. You pick one or the other, and there's reasons to have both. Now, the person who worked on all these NECs, Gerald Burke, he was a longtime NEC developer at Lawrence Livermore. He died in 2021. So in my opinion, that probably means there's not going to be a NEC 6. I don't know that for sure, but probably not. And of course, about 2 years ago, with the release of EZNet 7.0, the EZNet creator Roy Llewellyn, W7EL, he moved towards retirement, okay? So now we have somebody dead and somebody retiring. Is this going to be a problem for modeling going forward? Well, to me, not really. It turns out that some bug fixes and improvements have been made to NEC 5 by Roy and Dan AC6LA, in fact, the person who wrote AutoEZ. So it's not really dead. And I've also heard rumors that Lawrence Livermore National Labs is looking for people willing to take on support and enhancement of NEC 5.0. So if you're interested, give them a call. Now, the other thing that happened when Roy retired was EZNet Pro version 7, the Plus, became free, right? Not the source code, but the program. He had a couple tiers before that, a free program. I I think there was one around, what, $100-some, and then the $600 one, that's all gone, right? All that software is now free. And at the same time, or close, the license fees for NEC 4.2 and NEC 5.0, again, they're separate products, were reduced from $400 to $110, but they're still licensed through Lawrence Livermore National Labs. Okay, so this means that the pinnacle of NEC modeling software with EasyNEC now costs about $110 if you just want one engine, or $220 if you want to get NEC 4.2 and 5.0, and that was once $1,000. So I view that as pretty good news. W7EL, he's not really like retired and gone. He still sort of lurks in the background, fixes some bugs, but I know some people have said, hey, he never answers my email. Well, that's the one thing he doesn't do much of. Okay, now we could spend all day talking about NEC and EasyNEC, but that's not really the point. I did want to mention quickly that models between NEC 4 and NEC 5 you want to tweak them a little bit. We don't need to go into details on this, but while the NEC stuff up to 4.2, largely, you never changed your model. With NEC 5, some things are a little bit different. But if in the past you've shied away from modeling because of the cost or the performance or the size of the model you could take on, those days are gone. They've pretty much been gone for a number of years. Our new PCs, of course, are crazy fast. And what used to be, I think, a slog is now a breeze. I've got a whole bunch of reference information at the end of the slides here. We'll probably not get to the end given the time. But these will end up, I think, on Tim's website if you want to get to that information. Okay, back to AutoEZ. A software front end for EasyNEC versions 5, 6, and 7. Dan McGuire, AC6LA, created it. His little combination of words is automated use of EasyNEC. Dan lives out in California by the Bay, and it's hard to get him back here, so I asked if I could do this in his place. It does run on a PC under Windows. AutoEZ is an extension of Microsoft Excel, okay? If there's two things that Dan McGuire will go down in history for, it's his knowledge about transmission lines, which is just over the top, and his use of Excel. I've never seen somebody make Excel do what he can make it do. He uses Visual Basic extensions in the form of small macros, and that's how Excel ends up looking like AutoEZ. So now we have the power of the Excel spreadsheet brought into antenna modeling. And AutoEZ automatically executes EasyNEC underneath it. And in fact, EasyNEC really sits off to the side and is still visible. And in some cases, I kind of go back and forth between letting AutoEZ run EasyNEC or me manually doing it. And you just have to be careful you don't get in trouble where like you change something in EasyNEC that you really want to save, but then you run AutoEZ and it obliterates it, right? So you got to be a little bit careful. So the tool chain is AutoEZ with Excel in there, runs EasyNEC, and that sort of sits on top of NEC. So it sounds like a lot of parts, right? And like everything, you probably need some degree of knowledge of all the parts if you want to get the most out of it. So is this a steep learning curve? And I guess if I want to be truthful, the answer is yes. But to me, the rewards and the results are more than worth the effort. The ability to quickly and efficiently design and analyze and optimize based upon NEC has, I think, never been greater. And that's what led to the title about a revolution and not an evolution. This is also a great tool to learn about antennas. I like the phrase, the what-if process. You go through a set of antenna permutations and see what they do. Of course, like all the software we have to use nowadays, they act as amplifiers for our capabilities, but you have to learn them to the appropriate level. I guess what I would say is that if you're an EasyNEC user and you've got a little experience with Excel, I don't think you should have your head explode if you try to use AutoEZ. Now, AutoEZ is a licensed product, although there is a demo version, $79. But that license gets you all the PCs you own, free updates for life. Dan says he'll regret that someday. Money-back guarantee is another one of his terms. It has to be genuine Microsoft Excel. There's these compatible versions like OpenOffice or LibreOffice. Those don't work. his extensions to Microsoft Excel really have to be Microsoft Excel. And he's got detailed purchase requirements on the URL shown here. Okay, so what are the key features of AutoEZ? This now opens up the door to modeling with variables, modeling with formulas. I mean, duh, we're in Excel, right? We better see formulas. You can automate long runs of slightly permuted models and then optimize or analyze the results. And you can optimize the models. Another cool thing about AutoEZ is it accepts pretty much all of the file formats that have been around forever. So, of course, it accepts EZNet model files, AO, YO, the Brian Beasley programs, Yagi Windows, NeckWires, MMA&A, GAL, 4NEC2. Even it accepts 2 of the mechanical Yagi programs, Yagi Mechanical and Yagi Stress. So those can be read into AutoEZ. And then, of course, it'll drive EZNet with them, right? So it's sort of a free conversion to EZNet from these other tools. Okay, now an EZNet model is built from numbers and choices in a bunch of tables. And I counted them, I think there's 8. And things like wire sources, loads, or tables. And EZNet did evolve to include a lot of very powerful commands to let you edit, especially the wires, in a convenient way. But of course, a wire is described as 2 endpoints in space with an XYZ coordinate. And a lot of what turned people off about modeling is how do I figure out those numbers, right? So many feet over this way and feet, you know, this sort of thing. And I think that turns a lot of people off. But you know, in the old days, that's what you had to do with a calculator. Okay, let's look at an inverted V here as a nice example. Of course, there's reasons why we don't need to talk about why people might pick an inverted V just in general. Although if it's close to the ground, we know that it's probably a cloud warmer or an NVIS sort of antenna. Okay, I ripped off this picture from the K7MEM website, and here's the picture of our inverted V. We have an apex height. We have, he calls it the apex angle. I somehow like to think more in terms of the drop angle, which is the angle from the flat top down to the wire, which of course would be 180 minus the apex angle, that quantity divided by 2. You have the dipole length, each half, and we're going to model this at 80 meters at 3.525 megahertz. So here's, of course, where this is what turns people off about modeling. You got to get into usually some high school trig at some point. But we have an apex angle of 90 degrees, drop angle is 45. That puts that center point at 0x, 0y, h feet off the ground. And let's start off with 50 feet. And of course, it's going to be symmetric to the other side of the y-axis. Okay, and then there's the typical trig formulas. Now in EZNet, and this may be hard to see back too many feet, so, and in fact worse than that, will my pointer go here? Yeesh. We have here's the wires table, right? So there's 2 wires, and each is 1/2 of the inverted V. Each one begins at 0, 0, and 50 feet, and then they go off. We're all in the YZ plane, so the X dimension is 0. And they terminate at 47.3 feet and 2.6 feet off the ground. That's number 12 wire. Okay. Then the source table, that's where we're going to excite the antenna. That just says go to number 1, wire number 1, the end of it 0% of the way, and put in what was called a split voltage source. Now it turns out, for example, in NEC 5, you don't need split voltage sources. So if you had a bunch of old NEC 4 models or NEC 2, with split sources, which is how you had to do it back then when you wanted a source where wires met, NEC 5 doesn't have that. So that's one of those little tweaks you would have to make. Now, where did that length come from for the 2 side wires? What I did to make my life easy was I started with a flat dipole of the approximate length up at 50 feet, and I simply fiddled with the end length and tipped them down until I got it to resonate, 0 reactance. And then I used some very nice EZNet commands to tip the 2 wires down to a 45-degree angle each way, which leads to the 90-degree apex. And then, of course, once that was done, the resonant frequency changed a little bit, so I fiddled again with the length to get that resonant again. But it took a few minutes. I didn't have to break out the calculator. I didn't have to break into a sweat. But I had an EZNet model. Now, EasyNet or AutoEZ presents nearly the same tables, but now the spreadsheet cells can contain variables and formulas as well as numbers. So here's what the AutoEZ model looks like. There's some convenient constants that are provided at the top, like 2 pi, what a half wavelength is. This particular model is all in feet, by the way. So a quarter wavelength is 69.75 feet. But the big thing are the 3 variables. And again, it's hard for me to, my pointer here doesn't work. But the A variable is 50 feet above ground. The B variable is that 45-degree drop angle. And the D variable is the 66.7-foot side length, which came from EasyNet. So if we look at the AutoEZ wires sheet, notice it looks pretty much identical to EasyNet, right? We have 2 wires, each one has the same end, and then they have the different y-direct dimensions. So of course, at this point, you could say, Greg, what's the big deal? This just duplicates EasyNet. You're wasting my time, buddy. Okay, but notice that little formulas button with the red arrow. So if we click on that, now we go to a version of that same sheet, but now we're like in formula mode, and there's that big red cell there to tell us that, in which now what we can do is put our formulas and variables, and formulas with variables, into the cells in the spreadsheet. So for example, notice that the height on end 1 of both wires is equals A. And A, if you remember, was 50, the height of the apex. And then over on the end 2 of the wires, we have the formulas going back to using sine. Of course, most all computer-related trigonometric functions use radians, not degrees, so you got to convert that in there. But in any case, now we have a parameterized model, right? Then we can go to the calculate sheet, and of course, AutoEZ is in Excel, and it's organized as a bunch of sheets, right? Now, I sometimes call sheets tabs, but I think sheets is the official Microsoft Word. Okay, so for this guy here, we have one frequency, our 3.525 megahertz on the left. After doing, of course, calculate all rows, we see the resistance there, what is that, 49.13 ohms. The reactance is pretty much 0, so it turns out we're going to have a nice low SWR, which is one of the advantages an inverted V has. The maximum gain. Now, another nice thing about this is I clicked on including 3D data in calculations, and I also clicked in the far right, include the average gain test. If you're into modeling, one of the things that comes up sooner or later is this notion of the average gain test. And the idea is to make sure that you've got the most reliable and trustworthy modeling results. And that's done by doing this average gain test. And that largely looks for gain either escaping or artificial gain showing up. So you want that to be very close to 0 dB or an average gain factor of 1. So this is pretty good. And if you notice, the elevation angle of maximum signal is 90 degrees, so yes, this is a cloud warmer. So of course, now all this data is available in EasyNet. So once again, you might say, Greg, you're wasting my time here again. Well, now we can go to the generate test case dialog. And in this case, I put in a frequencies from 3.5 to 3.6 in 5 kilohertz step size. That's 21 total steps. And then you click OK. And then you end up with this. So what this represents, each line is AutoEZ running EasyNet once, capturing all the results, sucking it up inside, and filling up all the tables and everything else, okay? So this I would have had to do historically by myself and write the numbers down, and if I wanted to make graphs, do it. Now, in all fairness to EasyNet, EasyNet for many, many years has let you sweep SWR. But that's it. If you wanted to sweep gain, you were writing numbers down on a piece of paper. Here, AutoEZ does that all for you. Now, another sheet that's available is the pattern sheet. And as you can imagine, this shows your elevation azimuth patterns for the slice you're interested in. You can also click on a button up here and get the 3D plot as well. And of course, if you, in the middle there where it talks about test case, we have 21 separate test cases here, so you can move through all the slices. There's also a lot, on all these windows, there's some very good commands that let you add legends to graphs and copy them to the clipboard. So if your goal is to write a document or save your data somehow, this makes it a lot easier. Okay, another sheet, another tab, is the triple sheet. And here there's 3 separate graphs here, hence the name triple. The one in the upper left is the R, or the resistance and reactance at the first source. Now, a model might have many sources. The inverted V has 1. So we don't have to worry about which source are we talking about. But if we had more than one source, you could pick which one you want to investigate. But that shows the R and the X. And if you notice, again, I'm sure this must be impossible to see, but at 3.525 megahertz, the reactance crosses 0, and the resistance is right about 49 ohms. The gain is in the upper left, and then that SWR curve is in the lower left. Now, there's also a Smith chart tab for those who are into it, but we're not going to show that here. Now, rather than vary the frequency, let's hold that constant and instead vary the apex height. Remember, that started at 50 feet. Let's go from 50 to 120 feet off the ground in 5-foot steps. So the way we do that is, going back to generate test cases, we now can add a variable, A. And notice how it goes from 50 start value to the stop value of 120. The step size is 5. We're working in feet, so there's 15 steps. And over on the frequency side, that's the start and stop, or 3.525, so that's 1 step. Ultimately at the end here, you could fill up with 3 variables here, but when you think about it, if you had 3 variables, each one did 10 steps to investigate some part of your design, that's what, 10 times 10 times 10 is 1,000 models you would run. Now, EasyNet will do, or AutoEZ will do it. Maybe it'll take 5 minutes, but go off and have a cup of coffee. It'll run it all for you, collect the results, and let you analyze them. Okay, so with that, here's the results. Notice that the frequency column on the left is always 3.525 because we haven't changed that, but the height goes for the A variable from 50 to 120 feet, and then we can see what happens to the resistance and the reactance. The SWR, of course, turns out that it goes up. The max gain goes up. The takeoff angle of a maximum signal, though interesting as you would expect, drops from 90 degrees when the V is very close to the ground, a cloud warmer, down to 38 degrees. So again, EasyNet could let you do this. You just be running the model 15 times and writing it down and maybe making your own Excel graphs. Now you don't have to do that. What if I was thinking of putting the apex at 50 feet? Okay, now what would I have to do to change the length to bring that into resonance? So here I selected 3.525 at the A variable is 80 feet, and the D variable, which I wasn't changing, but I included it here, is at 66.76 feet. If I click on that button called Resonate on Selected Cell, what that tells AutoEZ to do is you are allowed to change the value however you have to in that cell until the reactance goes to 0, right? So we're going to resonate the antenna, or that source to be particular, specific, by changing that variable. And that's the D variable is the length of a side. So we do that, and it turns out the answer is 68.59 feet. And then if we look over here at the resistance and the reactance in the highlighted columns, 54.23 ohms and 0.03 ohms of reactance, or 1.085 low SWR. So again, we let AutoEZ do that, right? If you remember, what I said earlier was I was fiddling in EasyNet, changing lengths to get things like reactance to go to 0. Here I let the program do it. Now, instead of just selecting the one cell, I could select all of the cells in the whole D column and click on that Resonate on Selected Cell button, and now it ran EasyNet as many times as it needed to and fiddled with the length to bring all of the reactances down to 0. So here's a table of an 80-meter inverted V resonant at 3.525 megahertz with an apex height from 50 to 120 feet with all the lengths calculated for the lowest, or to be resonant. So they go from 66.76 feet at 50 feet to 69.43 feet at 120 feet off the ground. let's see here. You could also, of course, experiment with the apex angle, right? That drop angle. So in this case, I've got the apex height at 80 feet. The 45-degree drop angle is sort of where I'm starting. I've got that length. But now when I go to the Generate tab, notice that I'm varying the B variable, right, which was that drop angle from 10 to 60 in 5-degree steps. And then we get the results of that, and it ran it all itself. There's another very powerful sheet called the custom sheet or graph. And here, when you think about most graphs we generate in modeling, the x-axis is frequency. But oftentimes we want to look at other relationships between variables. So here, this shows the relationship between the maximum gain on the y-axis, and then the x-axis is the b variable, which is that drop angle, going from 10 degrees, meaning it's almost a dipole, right? We've only dropped 10 degrees on each side, down to 60 degrees, which we understand is going to be a bit compromising. And you can see the gain drop from about 6 dBi down to 4. And there's a snapshot button there that lets you save one graph, run AutoEZ again, and compare it against it. So again, this is stuff that we could always do if we want to just write down numbers, put them in Excel ourselves, and take the time. This graph compares 120-foot apex to an 80-foot apex V using that snapshot feature. Okay, some talk here about optimizing models, because this, I think, is a lot of fun and a lot of the power of AutoEZ. I think it's fair to say optimizing antennas is oftentimes more of an art than a science. This makes it fun. If we say optimize, we're optimizing something, right? We're not optimizing thin air. So you need some initial design, but that can usually be a reasonable guess. AutoEZ uses something called the Nelder-Mead simplex algorithm. There's details on one of Dan's web pages, and it also has its own Wikipedia page. I went into some detail here now that I'm going to skip about some of the pitfalls of optimizers, but one of the reasons why Dan picked the algorithm that he did was to, as best as possible, avoid some of these pitfalls. The main concern is you end up in a local minimum, right? You tell it to optimize the design, and it does, but it's only sort of in a part of the design space. But it turns out if some other part of the model was more radically different, it might even be better by however you define better. That would be like the global optimization. And that can be tough to do. And of course, if you think about a 5-element Yagi, right, we could say it has 9 dimensions. The length of the 5 elements, and you're probably moving the position of 4 of the 5, right? Usually you anchor like the reflector at 0, so the other 4 move. But that's 9 variables to optimize a Yagi. That's a lot of stuff. There's a lot of optimization algorithms. Dan did spend time trying to figure out the best algorithm. He used a lot of the built-in ones in in Excel and found them lacking. Let's sit here now talk about optimizing an OWA Yagi. I, over the last 10, 12 years, have been involved in probably about 20 OWA designs and optimizations. And we're looking to see, can we optimize them? Another thing that sometimes happens is somebody wants to redo their Yagi, but with a beefier taper schedule, right? They want to move to bigger tubing, have a higher wind rating, but now you've got to go and re-optimize the design, right? Because even changing the tubing stepping is going to cause the design to change. And when I've done this and compared previously optimized designs to EZNet, or to AutoEZ, AutoEZ has always done a very good job. You're not going to see 10 dB improvements, of course. They're relatively small, but it can do it. AutoEZ never gets stuck like in never-ending loops. It doesn't get stopped in those local minimas. So it does a good job. All right, let's see here. There's that line about there are no solutions, only trade-offs. I think that applies to optimization as well. This is a 6-element, 20-meter OWA Yagi on a 48-foot boom. And of course, if you know anything about OWA, optimized wideband array, you bring that D1 director close into the driven element, closer than you would if this were only a traditional Yagi, and that forms that coupled resonator that leads to a wider SWR response. So here are the variables for it. There's 13 variables. The offsets down the boom and the tip lengths. And AutoEZ, of course, will be adjusting the tip lengths. There's another setup sheet here where you can pick what it is of those variables you want to optimize, because maybe you don't want to optimize all of them. We're not changing the height above ground, right? That's fixed, 120 feet. We're not moving the reflector, that's fixed. And we're not going to move that D4 because we have a 48-foot boom, so we're not going to let it mess with that. Then you can go to the optimize sheet, and here's where you put in your frequency targets, and then there's a bunch of optimization objectives that you assign weights to, and that's, for example, where we see SWR and gain and front to back and front to rear. So by adjusting those numbers, you're putting in how much emphasis you want the optimizer to put in to improving that quantity, that quality. And then you turn it loose, and it's a lot of fun. I think it is, watching it do its work. Oftentimes, and you'll see the trade-offs, right? Like in cases like this antenna, you can get that SWR insanely flat, but you'll see the gain drop a little bit, right? And then you say, well, gosh darn it, now it's not as much gain as this other antenna. And if you back off on the SWR, you can maybe get the gain to go up. So again, there's trade-offs. After you're done optimizing, you go back to the calculate sheet. And then, of course, here we have the pattern sheet. You can run all the patterns. From the triple sheet, we have the SWR graph. Even though it looks high, the highest SWR there is like 1.16, right? So it's still relatively low, the gain, the front to back ratio. Boy, I'll say one more thing here. I guess we're about 350 here. Really, a lot of people I know have what I would call an aluminum tubing boneyard, right? Parts from all their antennas they've got, or estates of other hams. If you've got some booms and elements, you can literally whip up with AutoEZ good Yagis for any band you want. Use something like Yagi Mechanical to get the strength right, the wind rating you need for your area, and go in there and build Yagis. It's it's a little bit more than that, but it's really not that bad. Okay, there's a lot of examples online. I was going to mention other software by Dan. Maybe some of you know already, but we're pretty much out of time. And then there's a lot of other reference material at the end. And now this is the end. Thanks.